Okay, geometry, we're going to get moving now into section 7.5, which is the last section that we're going to be covering here in chapter 7. And this one kind of takes everything we've been talking about lately to the next level here by talking about proportions within triangles that are going to end up being similar to each other. So what we have here, first of all, theorem 7.4 just has one of my favorite theorem names of the entire year. It's called the side splitter theorem. So if we take a look at what's going on within this, I wish I could have drawn this live for you guys. I guess I can do that now. But if we started off with this big outer triangle here, triangle ABC, then what we essentially try to do is look at two of the sides here. All right, so I'm going to take a look at side AB, and we essentially then create point M just located somewhere on that side. Doesn't necessarily have to be a midpoint, and we split line segment AB by putting M there. And then we draw the line, the one and only line segment, coming out of point M that's parallel to this side down here on the bottom. And then this point of intersection over here on line segment AC, we call that one N. So we call this the side splitter theorem because we're splitting two sides of the triangle. We split line segment AB and line segment AC. Not necessarily in half, but we split it that way. Now, one of the sections that we didn't cover in this particular year was ways of proving that two triangles were similar to each other. Well, what I think you guys can see here is that triangle AMN, this little triangle right here, is going to be similar to the large outer triangle here of triangle ABC. And I think I could show that if I drew this out a little bit right there. Kind of, not perfectly. But basically, triangle AMN, the small one, and triangle ABC, the larger one, are the same shape but two different sizes. And when that happens, in fact, I should probably make that note right here, that triangle ABC, the larger triangle, is similar to triangle AMN. There's your similarity statement. And when that happens, guys, this proportion right here works out. The measure of line segment AM, which is this piece here, compared to the measure of line segment MB right here, is equal to the ratio of AN over here on the right to NC on the bottom right. The significance of this, everybody, might not seem like much to you guys, but the significance involves the inclusion of these two measurements right here, MB, which is this piece here on the bottom left, and NC, which is this piece right here on the bottom right. What's significant about MB and NC is that they do not represent complete side lengths within a triangle. The MB is just this little fragment right here. It's a little piece of line segment AB. And the same thing here happens with NC. So, in a way of looking at this, we really don't need this theorem because we already knew, because of this statement right here, that the ratio of line segment AM, which is the left side of the small triangle, compared to the measure of AB, which is the entire side of the left triangle, we already knew that that's equal to AN, which is the top right piece, compared to AC, which is the entire right piece. So this is something we already knew from similar triangles and our similarity statement. So in that regard, this theorem right here, the side splitter theorem, is almost like a corollary as opposed to its own theorem, but it is one that saves us some work. Now, the one thing I've got to caution you guys about as we move into our first example right here, most people grasp the side splitter theorem pretty quickly and pretty easily. The problem then is people learn it so well, and they think, oh, that's pretty simple, they tend to over-apply it and use it in a case where that doesn't quite work. So let me give you an example of what's going on right here. Now you'll notice, guys, I didn't write out the side splitter theorem in if-then form, but possibly the most important thing to note right here, it only works when that little segment that you've drawn inside an existing triangle, which in this case is line segment MN, this only works if that segment is parallel to the BC that I have on the bottom. And sure enough, that same thing happens right here. You can see with those red arrows. So that means, everybody, we can use the side splitter theorem here. I've got an x and a 12 on the top, and I've got a 2 and an 8 over here on the right. So the order in which you do this really doesn't matter, but you could say something like, dealing with the top side, 12, which is the big piece, over x, which is the little piece, would be equal to the same exact ratio done down there on the bottom. 8 would be the big piece, and 2 would be the small piece. This proportion here is correct, although, as I've tried to say this entire chapter, that is certainly not the only way you could have set this up. You could have done something like x over 2, this over this, is equal to a 12 over 8. That would have worked. Or you could have done x over 12 is equal to 2 over 8. With this particular proportion, let me think about this mathematically, guys. There are, let's see, 4 times 2, there's 8 different ways you actually could have set this proportion up correctly. There certainly are ways to do it wrong too, but 8 different ways that you could have done it right. So let's cross multiply here. We're going to get an 8x is equal to, and the 12 times 2 is 24, and then we'll just divide both sides by 8, and we're going to get x is equal to 3. And I would ask you guys for just a second before we box that up to think about whether or not that answer seems realistic. It does, and let's talk about 2 reasons why. For starters, the top side of this triangle is longer than the corresponding sides on the bottom. I know that because the 12 is longer than the 8. Therefore, this value up here that we got should be bigger than 2. All right, that's good to know. Looking at it another way, let's look at it here, guys. This little fragment down on the bottom, 2, is shorter than the 8 that it was directly next to. Well, that means that x here should be shorter than the 12 that's right next to it. So putting those 2 things together, I was pretty sure that x had to be bigger than 2, and I know that it's got to be less than 12. I feel really good about this answer, everybody. So, sorry about that. Let's box that up, and x is going to equal 3. Now, that is how the side splitter theorem works. But the mistake that I see all the time, I'm going to show you right now. You might not want to write this down, everybody. Like I said, people learn the side splitter theorem really, really well, so I start to see this proportion a lot, which makes some sense. People a lot of times want to tell me that 8 over 2, this side over this side, is equal to the ratio right here of 6 to y. Okay, people feel like they're going from the little triangle to the big triangle, so 8 over 2 equals 6 over y. I get why they think that. And now you end up with 8y is equal to 12, and dividing both sides by 8, boy, my y looks like a G there, you're going to end up with y is equal to, and 12 divided by 8, everybody, is 1.5. And if I ask you to think about whether or not it's realistic that y could have a measurement of 1.5, mull that over for a minute, most people recognize that that's not realistic. This piece right here has a length of 6. We know that. And it certainly seems logical that this piece right out here, which is parallel to it, would have to be longer than that 6 right there. And this is what I mean when I talk about people over-apply the side splitter theorem. So let me be clear and talk about why this answer here is wrong. The side splitter theorem, you guys, only applies on the 2 sides of the original triangle that are being split. That's this piece right up here because of that big dot there, and then this piece down here on the bottom, which is getting split right there. But this third side, the one that I've labeled in red, that's y over there on the left, that one doesn't get split by that new segment that we drew in the middle. The new segment is parallel to that. It doesn't get cut. So you can't apply the side splitter theorem in this particular setting. So I've got to undo a lot of what we just did. And let's talk about how we're going to do this one correctly. And the number one thing I can tell you guys, if you want to get this problem right, even though very few people take the time to do it, the best thing you can do is redraw this diagram as 2 separate triangles. So I'm going to redraw this, not quite to scale, with a big triangle and a small triangle. And let's fill in what we know. In the small triangle, I know that this side was 12, this side was 8, this side here was 6. In the big triangle, I know that the bottom side, which is from here all the way to here, is going to have a length of 10, which I got by adding together the 8 and the 2. And I know that this left side over here is y. That's what we're trying to find. Now, in terms of the top side, I'm pretty sure that this top side is 15. I got that by adding the 12 to this x right here, which I believe is 3. But I've got to be clear and say I don't actually know with 100% certainty that that 15 is right. If I made an error here, then that 15 is wrong. And if I use that 15 in my next calculation, well, I'm building a house upon sand, everybody, and that's going to end up being wrong as well. But now, when you look at these two triangles which are similar, most people now know where to go. The y on the left corresponds to the 6 on the right, and that ratio has to be equal to the 10 on the left, which corresponds to the 8 on the right. When you draw two separate triangles, almost everybody looks at this and goes, oh yeah, duh, this is how it works. So we'd cross multiply now, and we would get 8y is equal to, and a 6 times 10 is 60. We would divide both sides by 8, and we'd end up with y is equal to, if I'm not mistaken here, 7.5. And now when I ask you guys to consider whether or not 7.5 is a realistic answer for y, well, we were pretty sure that this y value had to be greater than this 6 right here, and this one is. Now, if you remember back to the answer that I had in red that couldn't possibly have been right, we got in red y is equal to 1.5. 1.5 is actually significant still in this problem. It represents the jump, the increase from this number here to this number right here. If you added a 1.5 to that 6, that gets you this answer here of 7.5. So that 1.5 had some significance in this problem, but it was not the measure of y. Okay, guys, that's the side splitter theorem. I don't know that another example is going to help drive it home for you anymore. You guys need to dive in and start doing some problems there, and I think you'll pick up on it pretty quickly. The second thing that we have to talk about today, everybody, is not a separate theorem, but it is a corollary. Second time today I've used that word, a corollary to the side splitter theorem. Just a little idea that takes an existing theorem and goes one step further with it. So our corollary to the side splitter theorem says the following. If three parallel lines intersect two transversals, there's the comma. So stop reading right there and draw a diagram. Well, lucky for you, it's your birthday, everybody. I got a diagram drawn for you, and look at what it has. Look at the red arrows. Three parallel lines, line AX, line BY, and line CZ. Those three parallel lines intersect two transversals. One of those transversals is line AC, or AB, or BC, whatever you want to call it, and the other transversal is line XZ. So if this happens, then here's what it says, then the segments intercepted on the transversals are proportional. So what's going on? This is usually one people can look at and kind of understand. We're saying with this statement right here, everybody, that the measure of AB compared to the measure of BC is proportional to the ratio of the measure of XY to the measure of YZ. It's kind of like the side splitter here, everybody. We're not dealing with complete sides of a triangle, but those sides are going to end up being proportional. So this is probably the big takeaway from this. You can draw a couple more. For example, you could also say that the measure of AB compares to, not just BC now, but the entire left-hand side from A to C. And I'm hoping you guys can tell me, or think on your own, what would correspond with this on the right side. What corresponds on the right with line segment AB on the left? That would be XY. And then on the right, what goes along with AC, which is the entire left side? That would be line segment XZ. So this is kind of another variation on this corollary here, and there's a third one. You could do the measure of BC compared to the entire left side, which is AC, equals, and again, think about this before you just wait for me to tell you the answer. What on the right matches up with the BC on the left? That would be YZ. And what matches up again with the AC over on the right? That would be an XZ. Okay, so this is kind of the third variation of that statement right there. All right, so 3 different ways of looking at it. So let's see an example with that, everybody. We're solving for x, and what do we see? I see 3 parallel lines because of the red arrows intersected by 2 transversals. So that corollary we just learned said that when this happens, all of these individual pieces are going to be proportional. The great thing about this, guys, what I really, really like, and actually this is kind of true going all the way back to the original side splitter theorem right here as well. What I really love about this is the proportion sets up almost exactly the way it looks. 10 is the top left number. 3 is a corresponding side right underneath it. And that equals, well, your top right number would be 12, and your bottom right number would be x. Now, if anybody was thinking, wait a minute, I would have done that differently, you could very well still get it right. The 10 on the left corresponds to the 12 on the right, if you want to look at it going that way, in which case then here is your second ratio. That now equals 3 over x. That works too. I'll show you why in just a second. Let's go back to the original one that I wrote and let's figure it out. The 10 times the x is going to be 10x. Look at me go. And 3 times 12 is going to be 36. And then we'll divide both sides by 10 and get x is equal to 3.6. Not an integer, but a pretty nice decimal to work with. If I had gone back to where I was in red just a moment ago with a separate proportion, well, check out this when you cross multiply. Now you get 10 times x, which still equals 10x. Same thing we had right over here. And the other cross product, 12 times 3, is still 36. Same thing you had right there. And when you divide by 10, yet again, you get x equals 3.6. So either way you guys want to set that up will work. Let me say again, in a problem like this, I do believe there are 8 different ways you could set up the initial proportion. I'm arriving at that number, guys, because you could start with any one of 4 different numbers, 10 or 3 or 12 or x. And then once you've made that choice with 4 options, there's 2 correct numbers you could then put underneath it to get going. The one thing you could not do, guys, would be starting it off this way, something like 12 over, think about that, it would be okay to do 12 over 10. What do they have in common? They're both top sides. It would be okay to do 12 over x. What do they have in common? They're both on the right. But it would not be okay to do 12 over 3. Those 2 sides don't have anything in common. 12 is top right, 3 is bottom left. So that is not an acceptable way of starting a proportion for this one. But again, you could have done something like 12 over 10 is equal to x over 3, and that is really the same as this proportion right here, guys. So lots of different ways to get there. Okay, so we learned one theorem, Theorem 7.4, which was the side splitter theorem, and then we learned a corollary to go along with it. The last theorem we have to talk about here today, you guys, is called the triangle angle bisector theorem. This book adds that triangle right there just for clarification, which isn't a bad idea. And this is one, everybody, that's a difficult one to write out in if-then form, and I feel like if we tried it, it still wouldn't help explain things at all anyway. So I'm going to go ahead and just illustrate what's happening here. We've got a triangle in blue, triangle ABC. And if you'll notice then, a red ray has been drawn coming out of point B. And the significance of those tick marks, everybody, right here, let me make those double tick marks. Dang gummit. All right, wait a minute, I wrecked the whole thing. Okay, so the significance now here is that those 2 angles, this would be angle ABM on top and angle CBM on bottom, those 2 angles are congruent. And that means, let's say this, everybody, that ray BM is an angle bisector. It bisects angle ABC. C. Going back to vocab from the beginning of the year here, guys, an angle bisector cuts an existing angle into two smaller congruent angles. And what the triangle angle bisector theorem says now, everybody, is that the original two sides of the triangle that did not get intersected by the angle bisector are proportional now with the two pieces of the side that did get intersected. You see why I don't bother to write this down, everybody? It's incredibly wordy. But here's what's going on here, guys. To put it this way, the ratio of line segment BA to line segment BC. Now, BA is this piece right here, and BC is this one. These are the two sides of the original triangle that were not intersected by that red angle bisector. But the side that did get cut by the angle bisector was AC. And with point M located right here, that creates two new pieces, guys. And the measure of the piece on top, AM, compared to the measure of the piece on bottom, MC, that ratio is proportional to the original ratio we started with. Some people like it better if we do it this way. If I were to put an X right here, lowercase now, and a Y right here, and then the two pieces of line segment AC, we now call those something like, let me put a W right here and a V right here, then the ratio, everybody, of X to Y is the same as the ratio from W to V. So you could look at it this way as well. X over Y is equal to W over V. That's really the exact same way of naming it. Just be aware, everybody. One thing I really hope you guys have down from the first semester, that when we're talking about lowercase letters, those are variables that represent a number. Over here on the left, when we did it with capital letters, remember the way we read this. This right here, BA, means the measure of line segment BA, and so on and so forth. Okay, so both of those are correct ways of interpreting the angle bisector theorem. Let's see it in action. So what do we have? We have a nice, pretty triangle in blue. It had three sides, and the 12 and the 20 are the two sides that did not get cut by this red angle bisector going down the middle. The bottom side of the blue triangle did get cut, not necessarily in half, but it got dissected as opposed to bisected, and the two pieces now are 9 and X. So we can use the angle bisector theorem to make a proportional, nope, not like that, to make a proportional relationship out of the pieces that still exist. Now, this is another nice one, guys, because you can kind of set up the proportion exactly the way the numbers appear in the diagram. 12 is the side on the top left, so I'll go with that. And the 9 is right underneath it. That would be equal to 20 goes in the top right position, and X goes in the bottom right. Now, I realize, you guys, the way I just did this is different than the way I just explained it right here. The way I explained it here was to use a ratio of the two non-cut sides. So that would have been probably something more like 12 over 20 is equal to, and hopefully you guys can tell me the second part, 12 over 20 would equal 9 over X. Both of these are going to work because your cross products on the next step are going to be identical. The one thing you could not do, though, everybody, think about this, is put 12 over X. 12 is kind of the top left number in the diagram. X is the bottom right number. There's no connection right there between the 12 and the X. Okay, but let's go back to where I was initially now. The 12 times the X here is going to get us a 12X. The 9 times 20 is 180, and we'll just divide both sides by 12, and that works out nicer than you might think. We're going to get X is equal to 15 for that value there. And of course, the second way I did it over here on the right, you're going to get the exact same second statement, guys. 12x is still equal to 180. Divide by 12 and you still get x equals 15. So there is definitely more than one way to skin a cat when you're setting up these original proportions. There's really 8 ways of doing it correctly right off the bat. And the last example I have for you guys is really the same type of problem as the one that we just did. However, it's got a little twist in it. And if I don't show you guys how to do a problem like this, people tend to panic just a little bit when they see one like this the first time. So what's going on? We have a big triangle. Oh, I had been drawing those in blue, everybody. Sorry. We've got a big triangle here that I'll put in blue now. And within that blue triangle, we have an angle bisector that's being drawn. And I had been drawing that angle bisector in red. So, okay, I should be a little bit more consistent with that. I know it's an angle bisector because these two angles are congruent. They each have just one tick mark. So, for that reason, we can use the angle bisector theorem. And you can do it in a couple of different ways here. The 8 is the number on the top left, so I would suggest that you start with that. Now, the number that goes underneath the 8 would be the length of this segment right here, which you'll notice has not been given to us. So let me be quiet on that one for just a minute and try to fill in what I do know. The top right would be this number right here, which is 6. And underneath the 6, right here, would be that y. Okay, so 3/4 of this weren't all that bad. The problem is what goes right here. And what we're about to do right now, guys, is a little bit of mathematical reasoning that I'm hoping you guys have picked up on in the course of the year. And if not so far, if you're not sure what goes there, hopefully you hear this explanation and it makes a little bit of sense. This entire bottom side, from the left all the way to the right, has a length of 21. Now let me throw some theoreticals at you. If y was 3, okay, I'm just making up a number here, guys. If y was 3, how long would this piece on the left here have to be in order to add up to a total of 21 if y were 3? Well, you would take 21 minus 3, and you'd get 18. If y was equal to 3, which I certainly don't know. If y was equal to 10, this piece right here would be 11. How? Because you're taking 21 minus 10, and that gets you the 11. That's usually some reasoning that people can understand pretty well. But the real issue here is we don't know what this is in terms of a constant. What it is y. So do what you just did. But do it now, instead of with a number like 3 or 10, treat y as a number, which it is. Okay? And then, what that means then, everybody, is that this piece here on the left is the total, which is 21, minus the piece that we were given, which is y. You've got to start thinking of y, which is a variable, as a number, because that's what it is. And this now is the best that we can do for the length of that bottom left side. It's 21 minus y. Okay, so that's one that takes a little bit of time to get used to. All right, guys, time to cross multiply. I'm going to do an 8y. Okay, that's my first cross product, is equal to, and I sure hope we've had enough practice at this. When I go to multiply 6 times 21 minus y, we need to recognize that 21 minus y is a binomial, and we have got to put parentheses around it, and then we've got to distribute that 6 inside there. Can't get these problems right if we can't recognize when we need parentheses and when we need to distribute. So 6 times 21, I do believe, is 126, and a minus 6y. Okay, we are going to add a 6y on the right, and then we have to balance that out by doing the same thing on the left. So those cancel. We're going to get a 14y is equal to 126. And of course, we're going to divide both sides here by 14. Those cancel. And we're going to get y is equal to, pretty darn sure, y is going to equal 9. Okay, and as we look at it, everybody, let me go to green here just for something different to pop out. We think that y is equal to 9 right here, and that would mean that this piece on the left, 21 minus 9, would have a length of 12 in order to add up to a total of 21. Well, does that make sense? Look at the 8 and the 6. The bigger number is over here on the left. 8 is larger than 6. So the bigger number here has to be located on the left as well. And sure enough, 12 is bigger than 9. The left half of this figure is bigger than the right. So that makes some sense. What else do we know? If you compare top and bottom, the 6 on the top right and the 9 on the bottom right, the bottom number, 9, is bigger than the top number. Does that same thing happen here? It does. 12 is bigger than the 8 that was up above it. So guys, this type of reasoning, this type of check, doesn't guarantee that you got your problem right, but it would in some cases guarantee that you got a problem wrong if it didn't match up in some of those cases. So that's a really good way to think about your answers after you get done with them. Okay, everybody, that is a wrap on our notes for section 7.5. Hopefully you didn't think that was too bad. And let's give the homework a try and let me know if you guys have any questions. Good luck, guys.